Right. Good day, ladies and gentlemen, and welcome to a new video. In this video, we're gonna get started on our new unit, Dynamic Earth, where we're gonna be exploring earthquake, volcanoes, tsunami, and the various layers and internal structures of the Earth. Page number 11 of your Earth Science reference table have this lovely diagram in front of you right now, and we're gonna be looking at the inner structures or the inner layers of the Earth. As you may already have learned from your elementary science or middle school science, the Earth has three main internal layers. The first is the Earth's crust, and then followed by the mantle, and then you have the core. Now, the core is divided into the outer core and the inner core. All right, so we're going to learn a little bit more as different layers other than these three main layers. Now, each of these three main layers can be divided into further layers, if you will, and we're going to touch base on those quickly and the differences between them and how all of these can create earthquake, volcanoes, tsunami, and the various things that we're going to be exploring in this unit. So this video is going to lay the foundational work on which we're going to build every other thing in the unit. So pay close attention, ensure you have your notes out, ensure you're annotating your reference table as we move along. All right, cool. So we're going to take the picture on the right, and then we're going to superimpose that into the picture on the left, which is your ESSRT page number 11. We're going to get started with the earth crust. Now, the earth crust can be divided into two groups. We're going to have the oceanic crust, then we're going to have the continental crust. So we have the oceanic crust here, and then we have the continental crust here. So it's not just the crust that we are dealing with now, but we are dividing it into two kinds of crust. Now, the continental crust simply means the part of the earth crust that carries the continent. Now, the continents are above water. The continent contains the mountains of the world, Kilimanjaro, the Himalayas, Mount Everest, all the Andes Mountains, the Rocky Mountains, all the mountains are all part of the continental crust. So the continental crust by default is thick. That means the oceanic crust is thin. All right, that's a very major important annotation to add to your reference table. The oceanic crust is just the part of the crust that is below the ocean. As you know, the ocean are a huge basin. They are a huge depression, which means the earth crust below them is just very thin, carrying the ocean. So oceanic crusts are very thin, while continental crusts are thick. In terms of density, the continental crust has a density of about 2.7 to 9.8 grams per cm cube, while the oceanic crust has an average density of 3.0 grams per cm cubes. Always take notes of the units. In sciences, we are very, very particular about the unit. Simply put, the oceanic crust is denser, which means it has more density. It is heavier for the if to find a similar word, heavier, more dense compared to the continental crust. So the continental crust is less dense. That is also another annotation you should add. Okay. Moving forward, we can also talk about their composition. We discussed this before on our Earth Science reference table page number, I believe, 13, when we discussed about mineral composition of igneous rock. We talked about mafic rock or ultramafic rock, and we see these rocks, they are much more denser and they are darker in color, right? And these rocks are rich in iron and magnesium and calcium, while felsic rock, on the other hand, are lighter in color, right? And then they are less dense in color. Okay, so we're going to bring those information into this reference table page number 11. So the oceanic crust is mafic, and we know that mafic rock are denser. That's the reason why oceanic crust are denser. So, which means oceanic crust will be darker in color, would be rich in iron, all right? Compared to the continental crust will be felsic, which means it will be lighter in color. It will be more granitic, for the lack of better word. It will be more granitic, which means it's more like a granite. While mafic are more basaltic, which means more like basalt. Going back to that reference table page number 13 we just looked at. So these are some of the major differences between oceanic crust and continental crust. Again, continental crust is thicker, while oceanic crust is thinner. Um, continental crust is more felsic and granitic, while oceanic crust is more mafic and basaltic. Continental crust is less dense, that's why it's floating. That is why it's more outermost in the layer of the earth. While oceanic crust is more dense with a density of 3.0 grams per cm cube, just below the ocean. By oceanic crust being mafic, it means it's going to be rich in more iron, silicon, and calcium compared to felsic granitic continental crust, which will be more rich in quartz and silicate. So simply put, all of these crust itself, the all crust itself is more made up of silicates, all right, which will be SiO2, which means silicon and more oxygen. Now let's move on. Just right below the crust is another layer, is part of the mantle that is referred to as the asthenosphere. All right, asthenosphere. Now, this is a semi-liquid part of the Earth's layer where we have all the lava and magma, where this is where they spew from. So it is not really a solid part of the Earth. It's semi-solid, it's semi-liquid. It's not liquid, it's not solid, it's just trapped in between, because this is where the lava and the magma exist and where they spew from. So that is the asthenosphere. All right. And you will notice also as we go deeper into the earth, depth is increasing. So as we move from the outermost parts of the earth and we move downward all the way to the middle of the earth, the depth is increasing. So depth is increasing. All right. Same thing with temperature. As you go deeper and deeper into the earth, temperature is also increasing. And then density is also increasing. So the density of each of these layer is also increasing. So all of these things are increasing as you go deeper and deeper into the earth. So let's look at the density of the mantle, for example. The density of the mantle is 3.7 to 5.6 grams per cm cube. That is denser than the oceanic crust, and the oceanic crust is denser than the continental crust. Then as you go to the outer core, which is this region here, which is this outer core that we're looking at here, has a density of 9.9 to 12.2 grams per cm cube. Again, that's a higher density. Then you have the inner core with a density of 12.8 to 13.1 grams per cm cube. So density is definitely increasing as you go deeper into the earth. Temperatures also increasing as you go deeper into the earth. The depth is also increasing as you go deeper into the earth as well. So those are some major takeaways that you should annotate in your reference table. Let's come back to the mantle. So we see that the mantle expands from here all the way down, and that the mantle can be divided into the upper mantle and the lower mantle. So it is part of the upper mantle that is semi-liquid, that is the asthenosphere that we just spoke about moments ago, that contains all the magma and lava. Then the lower mantle is much more solid, often referred to as the stiffer mantle in this case. So the mantle ends at a depth of 2,900 kilometers. All right, that's where the mantle ends. While the outer core starts from there, the outer core, which is liquid, remember it says fluid. All right, so don't forget, fluid simply means liquid. That should be something you definitely should add to your annotation. So the outer core is liquid and it starts from a depth of 2,900 all the way to 5,150 kilometers. Now this outer core is rich in iron and nickel. Iron and nickel. Nickel is Nickel. Same thing applies to the inner core. The inner core also is rich in iron and nickel, but the inner core is solid. The inner core is solid. I think these are the major takeaway from this earth science reference table. Ensure you annotate the bulk of these items in your reference table. All right, pretty much I think that's it. We're going to just quickly do a review of some questions and we wrap it up nicely. Question number 1 here says, compared to the oceanic crust, the continental crust is usually, so we are comparing two things here. We are comparing the oceanic crust and we are comparing that to the continental crust. So compared to the oceanic crust, the continental crust is usually, so we say the continental crust is what contains the continent, so by default is thicker so that it can stay above water to create the shapes of all the continents that we have in the world. So this continent also carries the mountains, so these mountains are high, so by default the continental crust should be thicker. So continental crust is thick, so option C is out, option D is out. The continental crust is less dense, yeah, definitely. So it's more dense, so that's why it should float and it should be on the outside of the earth, because as we go deeper, we said density increases. So if you are more dense, you sink to the middle, and if you are less dense, you stay on top. So the continental crust is the least dense layer of the earth. That is why it's all the way on the outside. So the continental crust is definitely less dense, it's thicker, and granitic in composition. Absolutely, it's granitic in composition. We said that earlier on. We said it's felsic, which means it's like a granite. So our answer here stands out to be A. It cannot be B because the oceanic crust is more dense. So B is out of the way. So that's the answer for question number 1. Easy breezy. Question number 2. Base your answer to the following question on the cross-section of the Earth below and on your knowledge of Earth science. The cross-section represents the pattern of seismic wave movement away from an earthquake. Point W represents a location at the boundary between two layers of the Earth's interior. So we're looking at point W right here is between two layers. Point X, Y, and Z represent seismic location on the Earth's surface. So we see X, Y, and Z right around there. So let's see what question 2 is getting at. Question 2 says, which data best describes the depth below the Earth's surface and the density of Earth's interior at location W? All right, let's look at location W again. Location W is right here. That looks like the boundary between, so this is the earth crust, so this is the mantle, so this should be the outer core, so this should be the outer core and this should be the inner core. So we are looking at a place, the boundary between the stiffer mantle and the outer core. That's where W is. So it's going to be the place between the mantle and the outer core. So this is where W is standing right in. So the depth around that would be 2,900 kilometers. 600 kilometers would not work. 1,000 kilometers would not work. C, that sounds like it. 1,500 already, we are going towards the boundary between the outer core and the inner core. That's way too deep, so D is out. So locations, option C seems to be our best answer here, but let's look at the density. It said density changes from 5.6 grams per cm cube to 9.9 grams per cm cube. Does that measure up? Yes. So we are moving from 5.6 grams per cm cube to 9.9 grams per cm cube. So that boundary right around there is changing from 5.6. So yeah, our answer definitely is C. Question number 3. At which depth below Earth's surface is the boundary between the Earth's outer core and stiffer mantle located? So it's asking for the depth between the outer core and the stiffer mantle. So I'm looking at the stiffer mantle and the outer core. Again, the depth is right around here. The boundary between those two will be right around there, which will be around 2,900 kilometers below the Earth's surface. Easy breezy. Question number 4. The diagram below represents a model of Earth's surface and internal structure. Letters A, B, C, D represents 4 different layers. Some depths below the Earth's surface are shown. So we see layers A, B, C, D right around there. And the question is saying which layer is inferred to be composed of solid nickel and iron. Solid nickel and iron. So we said it is the outer core and the inner core that would be rich in iron and nickel. However, we said the outer core is liquid, is fluid, so it cannot contain solid nickel or iron. It can only be the inner core. So the inner core definitely would be the layer D. How do I know? Because I know anything below the depth of 5,200, that 5,200 already we are sinking into the inner core. Anything below that depth. So definitely layer D here would be the inner core, right? Layer C here would be the outer core. Layer B here would be the mantle, right? And layer C here would be the asthenosphere that we already alluded to moments ago. Asthenosphere, and all of this will be the continental crust and oceanic crust. Again, we see that one of them is darker and one of them is lighter in color. So yeah, definitely our answer here would be option number D. Last question. The pie graph below represents the composition in percentage by mass of the chemical element found in Earth's layer. So we have that this Earth's layer is composed of oxygen, silicon, aluminum, iron, potassium, this, that. The composition of which Earth layer is represented by the pie graph. Well, it's mainly oxygen and silicon, so and that is our silicates, right? And then we said it is the earth crust that is mainly made up of silicates. The inner core and outer core is made up of iron and nickel, so our answer here definitely should be the earth crust. The outer core we said is iron and nickel. The troposphere is a gaseous layer around the earth, something we're going to look at when we look at the unit weather. And hydrosphere simply means water, and water is mainly made up of hydrogen and oxygen, H2O. So hydrogen is not highlighted here, so that couldn't be our answer either. So definitely our answer is A. Gentlemen, ladies, that's a wrap for this video, and I'll see you guys outside in class. Bye for now.